Hi, everyone, and welcome to the webinar. My name's Alex Magdans, and I will be your host today. Very glad that you could join us for this 30-minute discussion of systems modeling in the field of machinery design. Our main content today will be demonstrating how you can use SimulationX to model machinery dynamics faster and with better results. And we'll be doing that using the example of a scissor lift model that we'll build during the webinar. By the end of the webinar, we want to show you how you can use that scissor lift model to simulate tipping scenarios or other safety relevant situations. But before we get to that, we should introduce quickly what SimulationX is and who we are. SimulationX is a multi-physics system simulation tool. That means you can model the different subsystems of your machine, the mechanical, hydraulic, pneumatic, thermal, and controls, all in one model, and then calculate the interactions between those different subsystems. It's also a dynamic simulation tool, so we're calculating the machine behavior over time, and that's done using systems of differential equations that are created when we connect the model elements together. SimulationX has been used in industry for around 20 years, and it's widely used in Europe and Asia. Some of its notable customers in the heavy machinery industry include Liebherr, Palfinger, Tenova Tackraft, ABB, Siemens Minerals, Putzmeister, Remonta, and more. And very briefly, who are we? Well, there are two companies hosting this webinar today. The first is ESI Group. They're the developers of SimulationX, and the majority of the development team is located in Germany. Secondly, I represent the company XPI, which is the North American distributor and service partner for SimulationX. We work very closely with ESI to support SimulationX users in North America, and we have over 10 years of experience working with SimulationX. So this is the scissor lift that we're going to be working with today. Right now, we're viewing the CAD assembly of the scissor lift, which has been exported as a step file. This machine isn't intended to represent a specific scissor lift out there on the market. Instead, we thought it was just a nice generic machine for demonstrating how to convert a CAD assembly into a physics-based system model that you can use for virtual prototyping, safety testing, and more. So before we begin, let's take a look at how this scissor lift is built. We're going to be focusing on the scissor mechanics, so let's start there. At the bottom, we have a cart supporting the structure, and on the one side, the scissor arms rotate around a shaft that's fixed in place on the cart. On the other side, rollers allow the scissor arms to both rotate and translate in one direction. There are 4 levels of scissor mechanisms connected together in this machine, and on the very top is the aerial platform. Just like at the cart, at the platform, one end of the scissor can rotate around a shaft that's fixed in place, and the other end uses rollers to allow for both rotation and translation. The scissor mechanisms are driven by a hydraulic lift cylinder that spans between 2 shafts on the first and third scissor levels. Our goal today is to convert this CAD assembly into a multi-body dynamics model where we can simulate the forces, torques, etc. occurring on our mechanical system, together with the pressures and the flow rates of the hydraulics, so that we can run this machine through some virtual performance and safety tests. So let's dive into building our scissor lift model. This is SimulationX, what we're seeing now. Here we have the modeling area. On the right-hand side, we have the 3D view for viewing the multi-body system. And on the left-hand side is the library bar, which contains all of the collections of different components you can use for building your multi-physics model. Now, usually when we're building a multi-body system model in SimulationX, we connect together rigid bodies and joints from our library. So for instance, here I have this arm and a revolute joint. I can connect those together. I can make a copy of the arm and connect it on the other end of the revolute joint, and then continue building my model using the other rigid bodies and joints that I have available. But today we'd actually like to demonstrate the CAD import wizard, which helps us to import the entire multi-body structure from a CAD assembly. Now, before we begin, there's just a few things you should know about the import process and multi-body systems in SimulationX so that you can understand what's going on. Number 1, our multi-body dynamics model will primarily consist of rigid bodies and joints. So rigid bodies apply forces and torques resulting from their mass and mass moment of inertia onto the joints. And the joints provide degrees of freedom for the connected parts and calculate the motion quantities, that is, the translational and rotational velocities, positions, and accelerations that are resulting from the forces and torques acting on that joint. And number 2, we also need to understand reference frames. Now for this demonstration, all we need to understand about reference frames is that when we select a reference frame for an element, we're saying that the current element is connected to that other element. So for instance, we'll have a revolute joint here at this shaft, and when I import the scissor arm, I'll say that its reference frame is the shaft because it's connected to the shaft. This enables us to build the structure of the model. Okay, so let's jump in and start importing this assembly. You can access the CAD import wizard from the modeling tab of SimulationX. And now we can select the CAD assembly we want to import. In our case, it's Scissor Lift 2, and we press Open to start the import process. It takes a few seconds because it is a relatively big file. All right, so the CAD import wizard is open, and the first thing we're going to do is clean up the view a little bit. So I'm going to collapse the assembly structure in this left column, resize the columns a little bit, and then explain what we see here. In the first column, we see the structure of the CAD assembly. This is where we're going to select which parts to import. In the second column, we see the reference frames of those parts. Here, as we select our parts, we're going to choose the corresponding reference frame to automatically generate the structure of the model. And finally, in the third column, we see the SimulationX type. All of our parts are going to be of the type rigid body. But if we navigate to an axis that is part of our CAD assembly, for instance, the axis of this shaft, there we can see that by default, it has the type revolute joint, allowing rotation around that axis. But if I wanted to, I could make it a prismatic joint using that third column to allow translational movement along the axis. But in this case, we do want revolution around the shaft, so we can leave it as is. For this quick demonstration, I'm going to import the whole base cart as one solid body and not worry about its internal components. Instead, we'll focus on the scissor mechanisms. So let's connect our first scissor arm to the cart. We're going to begin with these inside scissor arms on the first level, and they're connected to the cart by this shaft, which allows them to rotate. So we'll need a revolute joint along the axis of the shaft to give them the degree of freedom to be able to rotate. To do that, we navigate in the tree structure to the axis of that shaft, select it, and then set its reference frame to be the base cart. By doing that, we're telling the model this joint is connected to the base cart. Next, we're going to select the shaft, the actual part, and say that its reference frame is its own axis, or the joint we just created. And now I want to connect everything else that's part of the level 1 inside scissor frame to the lower shaft. So I'll select these three other parts, that is, the left scissor arm, the right scissor arm, and the shaft for the hydraulic piston, and set the reference frame for each of these three to be the lower shaft. All right, let's see what we've done so far. So I'm going to press Preview. Okay, let's create a new 3D view and separate that into a separate tab so that we can see both the model structure and the 3D view at the same time. So a few things are noticeable. First of all, the diagram view of the model is a real mess. And secondly, most of our imported assembly is green. So let's fix those things. Back to our CAD import, we're going to change the diagram view layout so that rather than placing elements based on their position in the assembly, instead we'll use the dependency tree. So the connections between the elements will determine their position in the diagram. And next, most of our assembly is bright green, and that's because that is the color that is given when there's no color information for that part. If we take a closer look at our assembly structure, we can see that the scissor arms actually consist of the red arm itself and silver bearings, and these parts have different colors. So if we want to preserve the color information from the CAD assembly, we actually need to import those individual parts rather than the collection of parts that we've imported so far. So instead of placing a check mark for the whole right scissor subassembly, I'm going to place a check mark for each of its children. And likewise on the left-hand side. Now we can press Preview again to see the changes. Okay, so the diagram view of the model is much cleaner, and we've preserved the color information for the scissors. Like I said, I'm not going to worry about the cart in this demonstration, but in the same way, it would be possible to preserve the colors of each of the parts in the cart. Let's simulate this model to see what happens. If we press this record button, we'll also be able to play back the animation after. As we would expect, with nothing else connected, the scissor arms simply rotate down due to gravity. All right, I'm going to come back on screen and let's take a closer look at one of these parts. If we double click on the right arm, we get access to its parameters, and there we can see the mass and the center of mass that was determined by the CAD import wizard. Let's continue with the CAD import process, and now we want to connect the second level. The second level is able to rotate with respect to the first level, so we need a revolute joint right here at the axis of this shaft. So we navigate to that shaft, find its axis, and set its reference frame to be some component of the level 1 scissor frame. Then, just like with the first level, we find the shaft body and connect it to the joint we just created at its axis. And then we connect the rest of the level 2 scissor arm structure to the shaft, remembering to select the individual parts of the scissor arms in order to preserve their color information. And now we can preview again. And we simulate. And things are still falling down, just as we'd expect. Now you can see this process is a little bit repetitive. So while we finish off setting up the CAD import, I'm going to bring in Andreas Abel, who's the product manager of SimulationX, to explain how Palfinger uses SimulationX in the design of the aerial work platforms.
Right. Hello, everyone, and welcome to this little extra section in the webinar where I want to present a use case which is done by a customer, Palfinger, here in Germany. And this use case is about mobile working platform. You can see it here on the right-hand side of the picture. These mobile platforms are using telescopic booms in order to move operators in higher altitudes. And such platforms, they get more and more electronically controlled nowadays. So that means we will have ECUs attached to them, and these ECUs will control different aspects of the physical behavior, namely the mechanical kinematics of the machine, but also the working hydraulics. And so we can think of using simulation and simulation models in order to do controller development, testing and commissioning, and to do this preferably on a virtual model of the machine for obvious purposes. So for having less prototypes physically, for increasing safety and testing critical operations, also for managed variants. So when the hardware is the same, but different customers might require different software to be applied to the machine. And it's better to do this virtually than going to prototype deployment all the time. And last but not least, when you have it on a model and in a test environment, you're also able to automate your test and not necessarily have to do it through a human operator all the time. How did we implement that? So the implementation here is using a model which you see on the left-hand side. So there's a sketch behind which shows the machine. And overlaid on that, you see all those yellow elements, and these yellow elements are a multi-body system model done in SimulationX. So different components representing the kinematics, joints in between, etc. And this model we now use and deploy it into a real-time simulation environment, which is sketched here on the right-hand side. The model in itself is running in the core, the real-time simulator, which is in an iMachine. The real-time simulator connects to the ECU, where the control software is running, and the machine model is supplying sensor signals and is receiving back control inputs like valve currents in order to operate the machine. To the ECU, there is a operator panel connected, which allows the control to control the virtual machine. We also use the SimulationX model in addition to modeling the physical behavior. We use the 3D visualization of the model in order to make the operator see what's happening in the virtual test. So he will see the machine moving in addition to having the physical response to the controller. Well, in the end, when it's implemented, this has a number of benefits on the user side. First of all, of course, it becoming virtual. So you can do virtual commissioning, you get away from physical hardware. Second, it's a way to very quickly test new functions when new specifications come up or new customer requirements come up. So very often you will have the same hardware, but you will see that you will have different software which you would supply to different customers. One important aspect in this context, of course, is safety. And during the life cycle of the machine, you will see that the safety requirements might change, and such changes also might trigger needed updates into the software, and such updates would need to be tested again, and new software versions need to deploy to the machines, and apparently they need to be validated for that. Last but not least, we can use this in order to automate the test, manage test cases in the test environment, so that we have a nice possibility to free human effort here and do more things automatically. On the customer side, this is used for validating different aspects of the machine. One, I mentioned already, safety. Part of that is the stability of the machine, especially tipping scenarios, which of course should be avoided. But there are also other scenarios in the machine response, like for instance, the deformation, the mechanical deflection of the telescopic booms. And this will be impacted by the static load you put on the machine, but also by the dynamic load. And this is an important aspect which is interacting with the controller. And last but not least, I can also use that in order to check my dimensioning of the mechanical and hydraulic components, how they interact with the controls, and if they are properly sized in order to achieve the desired machine behavior. Thank you very much for listening to this short excursion into a customer use case about working platforms.
Well, thank you very much, Andreas. I appreciate you taking a bit of time to explain to us your work together with Palfinger Platforms. Thanks so much for being here. In the meantime, I've finished the CAD import process, so we can take a look at the model now and press the preview button and simulate it to see what's happening so far. Okay, so at this point, we have the mechanical structure imported. We have our CAD bodies, we have our rotational joints. So I'm going to simulate it once here to see where we're at. So we can see everything's falling down. So there's a few things we need to do still in order to have a functioning mechanical structure. So in preparation for this webinar, I realized it might be easier to understand if we reorganized that CAD import structure into something a little cleaner. So this is the same model structure, just reorganized. And here you can see the structure of the model, the base cart, the 4 stages of scissor mechanisms, and on top the aerial platform. And so now we have a mostly functioning mechanical structure. However, there's a few things we need to do to complete its functionality. We need to add constraints, we need to add the contact surfaces, and we need to add the hydraulics. So first things first, the constraints. Basically, what we've done with the CAD import is we've added the rigid bodies and the rotational joints, but there's also these 3 spots on the scissor lift right here, here, and here, where those mechanical components are connected together, and we need to add those connections in our multi-body system model. And we do that using constraints. So I'm going to copy in 3 constraints. There they are. And I'm going to connect them to the bearing on each side. So that's simply done by drawing a line from the connector of each constraint to the bearing on each side. And then we can simulate again. Okay, so it's falling down, which we expected. And now if we slow that down, we can see what's happening. So we go to our animation here, and we can see, okay, there it goes down. If we take a look, let's move this over a little bit so we can see what's going on. So if we zoom in here, we can see, okay, these are now connected together. That's good. But we are missing, for instance, down here, our contact surface. If we continue simulating, you can see it just falls right through. So we need to simulate, or we need to add into the model the contact surfaces, both on the base card as well as the aerial platform. So I'm going to copy in those now as well. Let's reset our simulation here. And I'm simply copying in pre-parameterized elements for the sake of the webinar so as to not take up too much of your time while we're doing this modeling. So up here, we have the aerial platform surface. So we're going to connect the rollers to the roller tracks so that those contacts are modeled. And we'll do the same thing now on the base card, zooming in down here. So we're going to connect the rollers here of that lower scissor mechanism onto the base card itself. There we go. And now we can resimulate. Okay, so we have some different functionality, as you can see. So let's take a look at that animation again in slow motion and go back to about the point where we were before, about here, and zoom in, and we can see that those contact surfaces, those rollers are now staying above the track, and we have a reaction force. So that is the contact surfaces are being properly modeled. So to wrap up this model, let's add in some basic hydraulics. So to do this, we're gonna use some elements that are existing from our library here. We're going to use a differential cylinder from the power transmission multibody systems library. We have a hydraulic differential cylinder right here that we'll add in. And I'm just going to spin that around a couple times. Connect it now to our system. There we go. And I'm going to add in the hydraulic components themselves. I'm going to keep it really simple. I'm going to use a proportional directional valve. Here, this 4-3. And I'm going to use a pressure source and a tank and just neglect the rest of the hydraulic circuit since our time is running somewhat short. Now, the purpose of these hydraulic models are various. You can use over 100 different elements here in the hydraulics library for modeling the hydraulic system. And as Andreas mentioned, some of the most common uses are for dimensioning the actual components of the real system, but also doing virtual testing of the controller and the operator system to see how it reacts to their commands. So we've got a basic hydraulic system set up here. We have a 100 bar going in as the source, the tank's at atmospheric pressure. Now I'm going to copy in a signal for the proportional directional valve so that we can see something happening during the simulation. And this signal is quite simply going to be a between -1 and 1 so that it just changes the position of the valve so that we can see something happening over time. And let's simulate that now after setting the stop time to 14 seconds. Okay, so we can see here how over that 14-second simulation, the hydraulic system allows it first to lower and then raise itself again. And that's just based off of the control signal that we've sent to the differential valve. So at this point, we have a fully functional model, and we can use it for all sorts of safety tests. We hope that by doing a little modeling here in the webinar, you've been able to see how quickly and easily you're able to build these types of multi-body and multi-physics structures using SimulationX. So now we'd like to demonstrate how you can use this kind of a model for safety tests. And to do that, I've prepared a little model here in advance. To demonstrate an interesting use of the model, let's assume the manufacturer wants to add an extension to the aerial platform and wants to check the safety limits for different lengths of extension. To do this, I've added this cuboid onto the aerial platform, and I've also added a global force at the end of the extension that grows over time. Now you may think it's stupid to have the extension there, it should be on the other side, but I actually tried that first and didn't think about the fact that there's nothing holding the ladder side of that aerial platform down. The rollers hold it up, but if you added an extension on the other side for this particular design, the platform would flip over. Another benefit of simulation. So to keep things simple, we're just going to add the extension to the ladder side. Now we can simulate to see at which force the scissor lift would begin to tip. And we can see, in this case, it's just over 4,000 newtons. The beauty is, all of this is parameterizable and can be automated, so I can change the extension length and run 100 different scenarios. That wraps up our webinar for today. I hope you found it insightful, and I would love to continue the conversation. We just have a couple minutes left for questions, so why don't we take one or two? All right, so let's take a look if any questions have come in here. And if you do have questions, feel free to post them in the Q&A. It's open right now. Let me start on the ones that have come in. So the first is about, or the first asks, what are the licensing options for SimulationX? What is a typical license? Well, the most common type of license is a network license. And that means that you're able to put that in your office, for instance, and have one seat or as many seats as you would like shared between the people that are working on this type of modeling project. And it's a tokens-based licensing concept, meaning you don't have to get each separate toolbox or each separate library. Instead, you get a certain pool of tokens, and then you're able to share those and switch between libraries as you wish and as your project requires, without as long as you have the necessary number of tokens available. Thanks for that question. Let's see if there's any others here. Again, feel free if you do have any more questions to post them. Next question is, what about training? What's available in terms of training resources? Okay, that's actually one of the nicer features about SimulationX is that they have quite significant resources available directly in the software for how to learn it. So there's significant documentation. Every single element has its own help file. There's also multiple tutorials included in the software that you're able to work through, and there's 400 example models within the sample browser. So you can, for instance, find a sample for a specific element or specific type of physics that you're trying to model and use that as your template or work from there. Excuse me. Okay, we also have a question here. How do I interface between different libraries? Okay, that's a great question. And actually, most of the libraries already have elements that are specifically intended for that. So you'll notice in the hydraulics and the pneumatic volumes and that sort of thing, any of the volumes already have thermal ports on them so that you're able to connect that to the thermal modeling part of the system. Anything that has a control interface, like the valve, for instance, has the signal block interface already on it. And all of the, let's say, actuators and that type of thing. So the pneumatic and the hydraulic cylinders, they have both the pneumatic or the fluid connections for connecting to the fluids libraries, as well as the mechanical connections. So all of those interfaces are already built into the libraries through specific elements. Okay, and then we have another question right here, and that's, how does SimulationX solve closed-loop chain problems in an inverse dynamic simulation? That's quite a specific question. We'd have to take a look at the problem you're trying to solve. But in general, this is equations-based modeling, meaning that you can set the boundary conditions that you're aware of, and it will solve for the other. It's not signal-based modeling that only has a single calculation direction. Depending on what you're trying to do, it may be a matter of simply setting the right boundary conditions and allowing for the solver to solve for the unknowns, or it may be a problem in which we actually use controllers or simply like PI blocks or PT blocks to translate from a current simulation or current situation, current scenario into the required inputs into the required scenario to achieve a certain output. Basically use a quasi controller to adapt the model to calculate the inverse solution. But I'd be happy to go through your specific problem with you and to come up with a solution to be able to solve that. Let's take one last look here. Any last questions? I don't believe so. If you do think of questions later, I'd be very happy to answer them by email or through LinkedIn. Thank you so much for attending today. I hope you found the webinar insightful and entertaining, and I'd be very pleased to continue the conversation with you one-on-one. Hope you're having a great day and wish you all the best. Thanks again.